We all just expect the lights to turn on when we flip a switch. It just works, right? But behind that simple act is this constant, incredible, delicate balancing act. And today, there's a new invisible guardian emerging to protect it all.
So let's dive right in with a question that, honestly, sounds completely backwards. We're all pushing for a cleaner future, right? More solar panels, more wind turbines. So why is the very backbone of our modern world, the power grid, actually becoming more fragile? How is that even possible?
Well, to get our heads around this, we really need to look at the difference between the old grid and the new one. Think of it like a tale of old-school heavyweights versus the new-school lightweights, and a critical piece of equipment that's quietly disappearing.
Okay, so this slide really breaks it all down. The old grid, it was built on a few massive spinning generators. I mean, we're talking literally tons of steel rotating in perfect sync. And all that physical momentum, it acted like a giant shock absorber for the whole system. Now, contrast that with the new grid. We've got millions of solar panels and wind turbines connected through these little electronic inverters. They have zero physical weight, no momentum, nothing to help stabilize the system.
And that physical momentum from those old heavyweights, it has a name, grid inertia. It's the grid's natural built-in shock absorber. See, if a big power plant suddenly trips offline or a huge factory powers up, all that spinning mass keeps the grid's frequency stable and prevents a total collapse. It's a property of physics born from pure, heavy, spinning metal.
So here's the problem in a nutshell. Every time we add a new solar panel or new wind turbine, we're swapping out a piece of that physical, stabilizing inertia for an electronic inverter that has absolutely none. We are, piece by piece, removing the grid's natural shock absorber, leaving it way more vulnerable to sudden shocks.
But, just as that old guardian is fading away, a new one is being programmed into existence. And this isn't a hero made of steel and spinning parts. Nope. This one is made of algorithms and code. It's kind of like a ghost in the machine.
So meet the Virtual Synchronous Generator, or VSG for short. This thing is a brilliant piece of software. It's basically a control algorithm that tells those lightweight, inertialess inverters how to act. It literally teaches them to mimic the stabilizing behavior of a massive, heavy generator, but without any moving parts. It's incredible. And its superpower has a fitting name: virtual inertia. It's the digital version of that physical shock absorber we've been losing. Inertia, created entirely from code.
Okay, so how on earth does a piece of software create a real physical effect? I mean, where does the energy for this virtual stability actually come from? Let's take a look at how an algorithm can actually keep the grid from collapsing.
This diagram really shows it perfectly. Think of the VSG algorithm as the brains of the whole operation. It's constantly watching the grid. The second it senses a disturbance, it instantly tells the inverter, hey, draw a burst of real energy, either from a battery or right from the renewable source, and inject it into the grid now. And it does this in a way that perfectly mimics the response of a heavy spinning flywheel, keeping the frequency stable. But, of course, that energy has to come from somewhere real. You've got two main options. You could borrow a little kinetic energy from the spinning blades of a wind turbine, but that's kind of limited. The real game changer here is stored energy, usually from huge batteries. That source is continuous, it's flexible, and it gives the VSG all the power it needs to act like a truly reliable, long-term shock absorber. Now you're probably thinking, this is great. Let's just crank up the virtual inertia to the max and call it a day. But it's not quite that simple. We're about to enter what you might call the Goldilocks zone of grid control, where the answer isn't more, it's just right.
See, here's both the magic and the challenge. A physical generator's inertia is fixed. It's built into the metal. But virtual inertia? It's just a number you can type into the code. It's totally tunable. And that flexibility is amazing, but it also creates a really, really delicate balancing act.
These two graphs show the trade-off perfectly. Okay, look at the graph on the left. As you increase the virtual inertia, that's the H value, you can see the frequency swings get much smaller and smoother. That's good, we want that. But now, look at the graph on the right. That same increase in inertia causes the power to overshoot its target way more dramatically. So you solve one problem, but you can actually make another one worse.
So what this means is that engineers have to perform this incredibly complex juggling act. They're trying to balance the system's dynamic response, its overall stability, and the amount of energy it has to pull from storage all at the same time. It's a tough problem with no single perfect answer.
Yeah, the design here is really a two-sided coin.
On one side, you've got the goals of the control system, what you want the software to do. But on the other side, you have the hard physical limits of your hardware, like how fast can your batteries actually push out that energy. A perfect algorithm has to respect both of those worlds.
So, if any single fixed setting is always going to be a compromise, what's the future look like? Well, the answer isn't to find one perfect number. It's to build a system that never has to settle for just one. We're talking about creating inertia on demand.
And this is really the key takeaway. The ultimate goal here isn't just to perfectly copy the old clunky physical grid. It's to use the flexibility of software to build something way smarter and more responsive than we ever could have before.
And this is how we're going to get there. Step 1, the grid is always changing, always in flux. That means step 2, a fixed inertia value is never going to be the optimal one. So the big breakthrough, step 3, is developing new VSG strategies that can adjust their inertia in real time based on what the grid actually needs. And that, step 4, is adaptive inertia, giving the grid exactly the right support at exactly the right moment.
It all really comes down to this powerful idea. We can absolutely build a stable, reliable grid that's powered entirely by renewables. But its foundation isn't going to be heavy, spinning steel. Its foundation is going to be smarter, more adaptive code.
It really makes you think, doesn't it? The solution to this massive physical engineering problem wasn't a bigger, heavier machine. It was a more intelligent algorithm. So the question I'll leave you with is this. What other invisible challenges out there are just waiting for a software solution instead of a hardware one?